This is Professor Kuehn. Let's continue our discussion of Pascal's treatise on the equilibrium of fluids. What Pascal is doing here, we're on page 179 of A Student's Guide to the Great Physics texts. What Pascal is trying to do is explain the hydrostatic paradox. And that is depicted in the top row of this figure, where he shows that it takes the same force to plug a hole in the bottom of a fluid-filled vessel, provided two things. First of all, the fluid is the same height in each of the vessels, and second, that the hole on the bottom is of the same cross-sectional area. So his main goal is to try to explain this hydrostatic paradox. What Pascal does is takes a diversion for a moment and talks about a slightly different situation, and he's going to use this slightly different situation to develop what's called Pascal's principle. What is this other situation that he's discussing? If you look at Roman numeral 8, so that's in the second row, the final column of that figure, where he shows that if you have a fluid-filled box and you cut two holes in the top, so you, in figure 8 on the right-hand side, he has a very wide cylindrical column welded into this large hole in the top, and he has a small cylindrical column welded into the small hole on the top of the box. He demonstrates that if you fill both of these vertical columns with fluid, they'll fill up to the same height. And he notices that if you think of, so if the right-hand column is filled to a height so that it weighs, let's say, 100 pounds of fluid, that will exactly balance this narrow column that has, let's say, only 1 pound of fluid in it. So it's an interesting situation where 100 pounds of fluid balances 1 pound of fluid. So why might this be? Why might 100 pounds of fluid be balanced by 1 pound of fluid? Well, this might not be so surprising to you if you remember our discussion of the lever. So let me just jog your memory with the principle of the lever. So you might recall that you can have a situation where a very heavy weight balances a light weight. So for example, you can have a heavy weight, let's say a 3 pound weight over here on this side, and it can be balanced by a 1 pound weight on this side. Why is that? Well, because the way the lever works out, if you take this force times this long distance, it's going to be exactly equal to this force or this weight times this short distance. Remember, that's the principle of the lever. So the idea that you can have a small weight balancing a big weight, we're already accustomed to. And here we're just going to think about that in a similar way, where we have a 100 pounds parcel of fluid balancing a 1 pound parcel of fluid. So you might want to start thinking about this like we thought about the principle of the lever. Now, with that in mind, let me box this off right here. So the idea is that Pascal is going to think about this fluid-filled box as a machine. So he's going to be using, so Pascal will treat the fluid-filled box like a machine. So this is how he's going to develop what we will call Pascal's principle. Okay. Now there's an idea here that's going to be useful in understanding machines like the lever or machines like this fluid-filled box, is the following: that machines, and in particular machines that lack friction. Technically speaking, no machines lack friction, but if the friction is so small that we can ignore it for the time being, then we can talk about machines that lack friction. They operate so that the work you put into them is exactly equal to the work you get out of them. Okay? The work that you put into a machine is equal to the work you get out of the machine. Later on, this idea is going to be incorporated by Hermann von Helmholtz into the principle of the conservation of energy. So this predates the work of Helmholtz, this predates the idea of conservation of energy, but the idea is that the work you put into a machine is equal to the work you get out of a machine. So how do we apply this to a machine like the lever, and how do we apply this to a machine like this fluid-filled box? So this is an important concept right here. Work in equals work out. Well, first of all, we have to remind ourselves what we mean by work. For those of you who have taken Physics 152, Physics 202, we came across the concept of work before. And for those of you who haven't, take this as your first introduction to the concept of work. So let's talk about what we mean by the definition of work. If we're going to say the work you put into a machine equals the work you get out of a machine, we have to know what we mean by work. Well, it's actually a fairly simple definition. The work that is done on something is equal to the force you apply to that thing times the distance through which it moves while applying that force. So for example, if we have a 1 pound weight, say this weighs 1 pound, and I lift it upward by 1 foot, I will have to do 1 foot-pound of work on it. Okay, pretty simple. We don't typically use the imperial system, the foot-pound, anymore. Typically we use the international system of units. So in that case, the force would be measured in newtons, the distance would be measured in meters. So in the international system of units, work is measured in Newton meters, not in foot-pounds. But you can imagine all kinds of different unit systems that one would use. In the international system of units, we use Newton meters, British system, foot-pounds. In any case, it's a force times a distance. Now, how is that concept, the definition of work, and the idea that work in equals work out, useful for understanding machines like a lever? Well, let's draw a picture of a lever once again. And I'm going to draw it in 2 different orientations. You'll see what I'm doing in a moment. Okay, so imagine we have a fulcrum right here, and this right here, the top one, is our initial position of our lever. And the idea is that you can apply a force to this side. We'll call that the input force. And in applying this force, you're going to move this lever down by some distance d in. So the work you put into this machine is going to be equal to the force you apply to the input side times the distance that the input side of the lever moves. And when that happens, of course, it moves down by some angle. We'll call this angle theta. Insofar as this lever is a stiff lever, it doesn't bend, that angle there is going to be exactly equal to that angle there. So when we move this down by a certain distance, this side is going to move up by a distance. And if you put this fulcrum a little bit closer to the right side than to the left side, then the output distance is going to be slightly smaller than the input distance. Okay, so you apply a certain force in over here, you move down by a distance d in. As a result, this side moves up by a distance d out, and it's going to push up on whatever is on this side with an output force out. Okay, now here's the idea where we're going to use this principle that the work you put into the machine is equal to the work you get out of the machine. Well, whatever work you put in is going to be equal to the work out. So in other words, the force that you apply on the input side times the distance you move the input side has to be equal to the force that is applied on the output side times the distance on the output side, right? Now, who cares? Why does this matter? Well, the interesting thing is this demonstrates why it is that a lever acts as a force multiplying machine. So let me rearrange this formula a bit. So force out equals force in. And then I'm going to divide both sides by the output distance. That's how I isolated force out on the right-hand side. And now notice that the force you get out is equal to the force that you put in, but it's multiplied by the ratio of d in over d out. So in other words, if, for example, if the distance you have to move the left-hand side of the lever was, let's say, 3 inches, and when this side moved down by 3 inches, this side moved up by 1 inch, so d out was 1 inch, then what happens is you get force in is equal to 3 inches over 1 inch. Whoops. Let me go back. I made an algebra error there. Okay, so force in times 3 inches over 1 inch equals force out. Or we can write that the output force you get is equal to 3 times the input force. Okay, so in other words, this acts as a force multiplying machine. If I wanted to push down with a force of, let's say, 10 pounds, I could lift something on the right-hand side that weighed 30 pounds, right? So this machine allows us to either lift or support a heavy object with a smaller force. And again, where does this come from? It comes from our definition of work as force times distance, and this more general principle that for machines, the work in is equal to the work out. Okay, so if you can understand this, if you get this, then you're going to be able to understand why it is that this fluid-filled box also acts like a lever. We're going to end up treating this in a very similar way that we just treated the lever. So let's pause for a moment and we'll come back to this.